To introduce us to Extension 2 mechanics, we took a look at this end of paper Extension 1 question from the 2012 HSC. It incorporates some 3D trigonometry that's now in our Mathematics Advanced syllabus and then moves into a rate of change question. It is Extension 1 content, but being at the end of the paper, it is a more challenging Extension 1 content, and it's a nice introduction into the motion that we're going to explore now through Extension 2 mechanics. So the first part of the question, it gives us a plane that is flying due north along this line U. And it's doing so at a constant angle of alpha that's been marked on the diagram. It also gives us an observer who is viewing the plane from point A along this line R, of which we don't know any further information about that particular angle of elevation, but we do know that the observer standing at A is on a bearing of 60 degrees from B and that they are 1 kilometre away from them, which has also been marked on our diagram. So this does give us our 3 triangles that we can now observe in order to solve the 3D trigonometry problem. So in this first part of the question, it's asking us to show this particular result for R, where we can see that the result occurs by taking the square root, and it's also relating cos and alpha, that angle of elevation, to R. So because it's incorporating those variables from all 3 different triangles, this is what's hinting to us that this is our 3D trigonometry problem, where we need to combine all of the information from those 3 triangles using our cosine rule. And the reason that I know it's the cosine rule is because of this square root symbol and the fact that we don't have a right angled triangle in the base, we have a non-right angled triangle that we're trying to work with. So the first step to answering any 3D trigonometry problem is to redraw all 3 triangles from our diagram. So our 2 angles of elevation, which are our right angled triangles in yellow and green, and then our base triangle in blue, which is our non-right angled base triangle, and making sure that we label all of our information that's given to us on them. It's also useful to go and label these common sides as well, so we can see where they match up in each of our triangles. The next step is to go and use those angle of elevation triangles to find expressions for these 2 sides that are matching up on this base triangle. So these 2 sides that we've called X and Y. And in triangle BGP that we've labelled in yellow, we can see that there are actually 2 expressions that we can find for side X. One where we're using right angled trigonometry with that angle alpha to find an expression for X in terms of cos alpha. And then the second where we're using Pythagoras' theorem because we have labelled all 3 sides. In triangle AGP, so the triangle that we have labelled in green, the only information that we have here are the labels on all 3 sides. So that means that we can only use Pythagoras' theorem to find an expression for y in this case. Lastly, we will now go and use the cosine rule on our base triangle, making sure to note that the side we are going to label as C is side Y, as it's opposite the angle that we know within that triangle, and side A and B can then go in any order. And substituting that into our cosine rule, making sure to be careful that we substitute the relevant expression from triangle BGP, as we did find 2 that are both valid, we do obtain the result that's required. The second part of this question is the motion part of this question, and it is a little bit of a trickier one There is some interpretation you need to do as you read through the information that's given in this bit. So the first part of this question says to us that the plane is travelling at a constant speed of 360 kilometres per hour. Thinking back to when we first labelled this question in part 1, U was the distance from B that the plane itself is actually travelling. So when they're giving us a constant speed that the plane is travelling at, that's the rate of change of the plane's displacement, or the velocity, which is occurring along this line that they have labelled U. So that gives us our derivative du on dt being equal to 360. The next sentence then asks for us to calculate at what rate, meaning that we're looking to calculate a derivative here, in terms of alpha. So we should be able to simplify our derivative as much as we can until all we have left is a value of alpha. And the rate that it's asking us to find is that rate of change of the distance of the plane from the observer. So the observer we labelled at the start of this question being located at point A. And the rate of change that they're asking us to describe is the rate of change of this distance here, r. So that tells us that the question is asking us to calculate the derivative dr over dt. So by starting our answer with listing the given derivative for the rate of change of the plane, that constant speed of 360, as well as the rate of change of the distance from the observer that we're being asked to calculate, we can now use the chain rule to make an expression that will find the required derivative. So we want dr on dt, we have du on dt, and in order to cancel out those values we don't need and put in the values we do, we need to calculate the derivative of dr over du. And that will come from the expression that we were given in part I, and hence why they make us do it first. So then substituting these two derivatives into our chain rule expression, we can simplify that down to this expression here, but it still contains a value of u. And the question's telling us we should be able to simplify that all the way down to alpha. So using the final piece of given information from the question, where they're asking us to calculate this rate of change when the plane has been travelling for 5 minutes, then that means that we have a time value of 5, and that allows us to find a value of u to substitute into that expression at that time value. So knowing that u is travelling at a constant speed of 360 kilometres per hour, but we're now working in minutes, we can change that rate into a rate value of kilometres per minute just by dividing by 60, and then multiplying that by the number of minutes that we've travelled for gives us a u value of 30. And substituting that into the expression will leave us with a derivative in terms of alpha, and that is the final answer for the question.